Welcome back. This is lecture 13. With lecture 13, we are introducing trees. We finished the linear structures with sparse arrays, and now we're going to be talking about trees. The idea behind a tree is it's going to be a very recursive structure. We talked a little bit about how with linked lists, we could have viewed it as a recursive structure or a non-recursive structure. Trees tend to usually be viewed more in a recursive manner and have algorithms that run recursively. And the reason is because of the way trees are set up. So if you're at all familiar with the Dewey Decimal System of a library, or if you're not, it's a system for categorizing books. What you'll have is that every book will have a call number. And so once you have that number might be something in the 100s, or it might be something in the 200s, or 300s, or 400s, or 600s. You know, you have basically all possibilities from 0 through 999 in these large categories. And so, for example, the 600s, anything in there tends to be science and engineering and applied technology. And so, for example, you might have the 620s, which will be autos. And then you have, say, I believe it's 670 is woodworking. I used to work in a library, so I vaguely remember some of this. 670, for example, is a particular category. And then within 620, you have 622 would have some special meaning. 629 has some special meaning. Those are the auto repair books. 629s tend to be car-related stuff or car repair. So you can basically have the idea here, as we're seeing, of at any given spot, there's a number of choices you can make. So when you know it's a 620 number, you can say, well, it could be 621 or 622 or 629. And the concept then is that at any given location, there's a number of branches to the next possibilities. Similar to a directory structure, say in Unix, as you've been doing your MPs, where when you're in any given directory, there might be a number of subdirectories you could enter from there. And so you can think of this as the top level directory, and then this is your various MP directories. Within the MP directory, you maybe have, here's my solution, here's my testing, and here's whatever, however you divide things up. But you have basically at any given spot a number of places downward you can go. The example in the textbook is one of the animal kingdom, where you have mammals animals, and from animals you'd have categories of mammals and birds and fish and so on, and then from mammals you have then specific types of mammals and so on. So all these structures have this idea in common. All these ideas have this similarity, which is that you have these nodes with these sort of fan-outs into lower choices. And in general, that's how trees are set up. So the idea of categorization and subcategories and further subcategories is one nice way of introducing a tree structure. In general, though, the way we tend to have these set up is we will have a particular node, which we'll call the root, the top node of the tree, and then a series of these as well. There. And these are called subtrees. And this entire structure is known as a tree. The idea being that these subtrees themselves, we can think of these as the categorization. So in say, the library example, you can say, well, given a starting point, then these are all the 100s, and these are all the 200s, and these are all the 900s. Or if this was a 600 starting point, these would be the 610s and the 620s and all the way up to the 690s. So you can have things arranged in that fashion. Each of these subtrees is itself a tree with its own root of a subtree and then a number of subtrees coming from that. Each of which has a root and a number of subtrees, now to the point where I can't really even draw this anymore because it's too detailed. But the idea is that this structure is a root pointing to a number of collection of subtrees, each of which itself follows that same pattern of a root and subtrees, each of which is a root and its own subtrees, and so on. Down to the point where you just don't have any children, or down to the point basically where a tree doesn't exist. A subtree is null. And so that's the other thing a tree can be. You either have an empty tree, or you have a root element with a bunch of subtrees. And how many subtrees do you have? Well, maybe none. So if you have a root and no subtrees, that follows this pattern, or a root and one subtree, or a root and two subtrees, and a root and 20 subtrees. The point is a tree is defined as either being empty or being a root node and then pointing downward to a collection of 0 or more subtrees. And then the subtrees are defined the same way. So that's the idea of a tree. Or another way to think about it is the linked list had a pattern set up where you had these dynamic nodes, and every dynamic node had a predecessor and a successor. And it was basically the same thing with the array cells. Except for the very beginning and very ending cell, you can think of every cell as having exactly one node before it and exactly one node after it. Where for the tree, you have one node before it. Each of these roots of these subtrees has as a sort of above it node the root here. So this is the node above this. This root node is also above this. This root node is also above this. So there's one predecessor for each node, and yet a given node has many successors. And so you can think of and if you imagine following this kind of a structure down, you go from node to node to node to node to node. It's like a linked list, except you have many linked lists tying together at a common starting point. And so that's really how this can be seen. It's like a linked list, but instead of each node having one successor, each node has many successors. And so you have then the idea of a node with a given number of nodes that succeed it, and each of those has a number of nodes that succeed it, and each of those has a number of nodes that succeed it, and so on. And so you end up then with a picture much like this, where you say we can draw the subtrees just as triangles. When we look at an actual real example, the entire thing from start to finish, we'll have a structure like this, where we will say, okay, we've got this, and here we have something such as that, and then here we have something like this, and then maybe there's 3 of them here and 4 of them here. And however many of the nodes succeed each one is entirely up to you. Here's a node that has nothing succeeding it. Here's a node that has 4 nodes succeeding it. So, but there's an example of a tree structure. Like I said, it's much like a linked list, except each node is succeeded by many. And so usually we are pointing, if we're going to draw the arrowheads here, we'll have them pointing downward. And I could draw the rest of them, but I won't. And then, of course, just as we have a head pointer for the list, we usually have a pointer called root to the top node. Now, there are a number of definitions we can deal with here. These definitions are going to be on pages 96 through 103 in your book. But at this point, I asked Charles, and neither of us is actually sure if you were all required to get the textbooks or not. I have traditionally gone through them. This semester I was trimming it from the local lectures because these are things that you should have seen in a prerequisite discrete math course, CS225. But I'm not being entirely sure exactly not being entirely sure exactly what you've seen in whatever discrete math course you may have taken. I'm going to quickly run through some of the common definitions here on the lecture video at least. The most common ones I would go over anyway, and those are, all these definitions are going to be sort of a mix of genealogy, which is things like family trees and such, so you'll have terms like parent and ancestor and descendant and child and sibling, and biology. You'll have actual tree nature terms, so you'll have terms like root and leaf and forest. And so most of our terms tend to be a mix of those two fields, genealogy and the tree biology. So instead of calling these predecessors and successors, when we have a structure set up like this, just as an example, generally this is called the parent, and one of these would be called the child. And so we have here the parent node. Let me label these W, Y, and Z, and there's X up there. Generally, that doesn't even begin to look like a Z, does it? We'll call this O instead. There we go. So we have the node containing X is the parent of the node containing W. It's the parent of the node containing Y. It's the parent of the node containing O. Each of these 3 nodes has X as its parent. These 3 are the 3 children of X. And so we have that relationship there. Those are important definitions. You also have the idea of, you can extend this further upwards, where we have the terms descendant and proper descendant, which aren't quite as important, but I will perhaps use them from time to time, so I at least want you to know what they mean. And the idea is that generally we're saying that a node is a descendant. The book is a little bit more formal, but just to be a little bit informal here, we say that a node is a descendant basically if it's in the subtree rooted at X. And so anything as however far this deep goes, however far deep this goes, all these nodes that are inside the subtree that x is a root of are all descendants of x, including x itself. And so the difference between descendant and proper descendant is we don't say a node is a proper descendant of itself. And so we could say x is a descendant of x because x is in the subtree, but we really generally don't want to call x its own descendant, so then we have the term, well, proper descendant means you don't count x. And likewise, if you're going to use the terms ancestor or proper ancestor, same idea. The term proper ancestor simply means don't count the node itself. But if we say an ancestor of a node, we're saying all the nodes upwards from where we're counting up to the root of the tree. And so the ancestors of this node would be itself and y and x. And so therefore the ancestor of w would be w and x. And again, when we're talking about proper ancestor, we don't count the node itself. But these are not too important. If I happen to throw out descendant or ancestor, you should know what they mean. But the parent and child there are the much more important ones. Another irrelevant one is the idea of sibling. Siblings are nodes with the same parent. So W, Y, and O in this diagram are all siblings because they all have the same parent. These two nodes are not siblings. These two nodes, though they're on the same level, are not siblings because they have different parents. And then you'll sometimes see less frequent terms like uncle and cousin, which would mean exactly what they mean in real life, but we're not going to get into that here. The analogy when we said we call this the root, and we will talk of different roots. The entire tree has a root, and then when we start talking about individual subtrees, we'll often say root of the subtree. So the subtree containing y and these two nodes, the root of that subtree is y. The subtree containing these two nodes, the root of that subtree is o. This subtree contains only the node itself, but its root is w. And so we'll speak often of the root of the whole tree or the root of the individual subtrees. And that way we can make that recursive structure known. The other thing you have here is the idea of a leaf. A leaf is simply a node with no children. So W has no children. None of these nodes down here have children either, so they are all leaves. Y and O do have children. Y has 2 children. O has 1. So those are not leaves. So we have that term as well. The other two big definitions that we tend to worry about for trees themselves before we get into specific kinds of trees are height and depth. The height of a node is going to be the longest path from, I should say length of longest path. From the node to a leaf. So when we talk about the height of a node here, for example, these three are leaves. The length of the path to those nodes is 0 because they are leaves. Likewise, W's height is 0 as well. Y's height is 1 because the length of the longest path from those nodes to Y is, or from Y down to a leaf is 1. O's height is 1. X's height is 2. We can get to a leaf in one edge, but the longest path will take, there's 3 different longest paths that get us down to a leaf, and those are all of length 2. So the height of X would be 2. And we can talk about the depth of a node. And the depth of a node will simply be length of path up to the root. So the root has depth 0, the root's children have depth 1, their children have depth 2, and so on. And so when we deal with that here, we have these are depth 1, 2. You can sort of count downward by level and say just depth 0, depth 1, depth 2, depth 3, depth 4, and so on. When we talk about the height of a tree, we mean the height of the root. And so the entire tree has height 2 because its root has height 2. And when we talk about the depth of a tree, we mean basically the same thing. For a whole tree, the height and the depth are the same thing. Because for a tree, we're saying, what's the depth of the deepest leaf? And that's going to be equivalent to that path that goes from the root to the deepest leaf is going to be the same as the height, the path that we take from the leaf up to the root. So when we talk about a whole tree, the height and the depth are considered the same. But when we talk about individual nodes within that tree, the height and depth are different because we measure the height from the bottom and we measure depth from the top. Where when we talk about the whole tree, we're simply saying, well, for the whole tree, we're always concerned about the longest path in the tree. So the height from the deepest leaf up to the root is the same as the depth from the root down to the deepest leaf. It's the same term, just going and traversing the tree in two different directions. So the tree itself has the same height and depth, but individual nodes within the tree could have different heights and depths. And as a great example here, W has a depth of 1 but a height of 0. So those are some quick terms that you need to know as far as trees go. Now as far as types of trees, the most generic kind of tree that we do in computer science is we're talking about an unordered tree, where if this is your tree setup, A, C, and D, that is exactly equivalent to A, D, C. If they're in an unordered tree, those two are the same. That is, the order of the children does not matter. And that's the idea here. Children order is irrelevant. Where for an ordered tree, the order of the children matters. So just as a quick example, if this is the boss and the 3 children in the tree are 3 employees in that boss's division, if the procedure for promotion is whoever's been there longest gets promoted, you might say, well, I'm going to arrange these in terms of the leftmost, we arrange from left to right, highest to lowest seniority. So if person B quits, A gets promoted because A is on the left side. And then now D is the highest in seniority, and then C, and then whoever else. An arrangement like that, keeping the children in a particular order would be important, because A being before, or C being before D or after D would make a difference. Here we're saying C has higher seniority, there we're saying C has lower seniority. So there's an example of an ordered tree, a situation in which the order you keep the children in might matter. Where other applications, we may say, listen, I'm just concerned with storing the children. What particular child goes in which slot, it doesn't really matter. We just simply say, B has children A, C, and D. Who cares what order you store them in, just whatever order you happen to insert them, but it doesn't really matter. So an ordered tree then is slightly more specific because now we're saying that order matters. From there, we can go to a k-ary tree. So when we deal with a k-ary tree, we say maximum of k children per node. So that simply means when you draw out the tree, well, you say in advance, no node can have more than k children. So in a 3-ary tree, no node can have more than 3 children. In a 6-ary tree, no node can have more than 6 children, and so on. And the most common version of that is going to be a 2-ary tree, which is more commonly, far more commonly called a binary tree. And that's going to be what we're dealing with almost exclusively for the next bunch of lectures. Binary tree, and the idea of a binary tree is that we have a max of 2 children per node. Every node will have 0 children, in other words, a leaf, or it'll have 1 child, or it will have 2 children, but no more. And so we will deal with that kind of tree as well. And so we're going to be looking at binary trees pretty exclusively, though at the end of, as we finish up the lecture today, we will go back and talk a bit about different implementations for different kinds of trees as well. We do have the idea of a binary tree. There are 3 special kinds of binary trees that I'm going to go through really, really fast. Don't really worry about these at all, other than, I might throw out the term, know what it means, but we're not going to test you on these terms. Don't worry about it. Nor are we going to test you on ancestor or descendant. So you just should know what those mean. So if we ever use them, you're familiar with them. We have the idea of a full binary tree, and that means every node has 0 or 2 children. So for example, a tree like this, where if you have any children at all, then you have both children. And there are no nodes that have only 1 child. That just happens to be called a full tree. It doesn't really come into play too much for anything specific that we're going to look at in lecture. But But anyway, that's a tree definition worth familiarizing yourself with. We also have the idea of a perfect tree, and that's a tree like this, or like this, or like this, where we basically say down to a given level, we have all possible nodes. And I'm not even sure if Charles is going to be able to make that tiny diagram there. But anyway, we simply have here the idea of for height h, for a given height h, we have 2 to the h, for example, here height is 1, so we have 3 nodes. Here height is 2, we have 7 nodes. So we have here 2 to the h plus 1, that's the pattern, minus 1 nodes. Height is 3, that would imply 2 to the 3 plus 1, which is 2 to the 4 minus 1 nodes, 15 nodes. And so that comes into play, that's accurate. We're basically saying down to a given height, all possible nodes in that binary tree. So I should say this is really a perfect binary tree. And the height of this is as perfect as things get. The height of this is going to be on the log of n, where n is the number of nodes. And you can see that if you reverse this, if you say n equals, then if you solve for n, you'll have that n is roughly, or h is roughly log n. And that's going to come into play later on when we talk about binary search trees. The idea will be that the average tree will be closer to perfect than you'd expect. And the average tree will have a logarithmic height rather than a linear height. But don't worry about that yet. And then complete trees we will talk about later, much, much later in the semester. But a complete binary tree is simply one in which it's perfect down to a given level, and then now on the level right below that, we're inserting nodes from left to right. So you simply say, I can't skip over this node. I have to insert the far left, then the one right next to that, then that one, then right next to that, and so on. So we build across from left to right, and then drop a level and build across from left to right, and so on. So a full binary tree, perfect binary tree, and complete binary tree. Complete binary trees will come into play later on. For now, I just want to introduce those definitions in case you don't have the book. I'm not sure if you do or not. Don't really worry about these too much. Just toss them in the back of your mind as, oh, there's these terms, but don't worry about them too much. We're not going to say, explain what a full binary tree is or anything like that on the exam. As far as the ADT goes, now that we've kind of done a whirlwind bunch of small little definitions, as we said with the linked list before, there tends not to be a standard tree ADT, just like there isn't a standard linked list ADT, standard list ADT or anything like that. Just a collection of methods that tend to be useful. And there are ones that tend to show up more commonly than others. Like I said, stack and queue are a little bit more standard. For trees, certainly there is not a standard ADT because you have all sorts of different kind of trees. We've just looked at a bunch here. So for, say, binary trees, for example, you might have a function called left and right, because we'll commonly refer to the two children of a binary tree as the left and right child. So you might have left and right as your functions to return the left and right children of a binary tree node. Where in general, you might instead have a function child of I, where you pass in a particular index and return that child. So if you have a 5-array tree, you could pass in child of 1, child of 2, child of 3, child of 4, or so on. And that particular index there would indicate which child you want. You might want to detect the height of a tree. We have the standard insert, find, remove functions. You might want to do something such as copy or copy subtree. The list can go on and on. Anything you can think of doing to a tree, you can perhaps do. What we're going to look at next lecture is some standard ways in which the tree is traversed. So if you want to print out the whole tree, well, a list was easy. You go from front to end. What order should we print out the tree in? We'll talk about that in the next lecture. So there are a number of different functions, and so I'm not really going to spend any time talking about the ADT, but I at least wanted to address the notion for at least a minute or so, and say there are a number of different functions you might do. And we will discuss different functions as they become useful. You could write your own as well, but there are going to be many different relevant kinds of things you might do on trees, and some of them will depend on what kind of tree you have. Because, like I said, for example, knowing you have a binary tree would perhaps change your interface a little bit. Our concern is going to be more how things get implemented. And we're going to look at a binary tree first. When I draw a tree like this, where we have, for example, A, X, B, Q, W, K, J. There's an example of a tree. And the question that would be, if it's considering it's a binary tree, that means no more than 2 children, how might we implement this? And for that, we can kind of look back at the linked list and say, well, we said there was a similarity here between this and the linked list, where with binary trees, you have a 1 predecessor and 2 successors, and for linked list, you had 1 predecessor and 1 successor. So let's kind of use this idea and say, well, let's just have a node just like the linked list node, but with 2 pointers instead of 1. We have the left pointer, we have the right pointer, and then we have an element field, ELEM or element or whatever you want to write there. And that's typically how we handle binary trees. And so we can then say, well, I can draw here X, and I can draw here B, and I can draw here Q. Whoops. Q's left child and right child will be null, because Q has no children, as we can see in the diagram. Here we have W. W's right child is null, but W's left child will point to K. K has no children in our picture, so both of those would be null. And likewise, then B's left child is null, B's right child is J, and J has 2 null children. So this conceptual picture tends to be implemented like that. And as I said, usually we have some sort of a root pointer pointing to the first node, just like we had a head pointer pointing to the first node of a linked list. Now, as we start dealing with binary trees over the course of the semester, I'm going to tend to just always draw them like that. Sometimes I won't even bother putting the arrowheads on. In fact, usually I won't. It's a lot easier just to draw circles and lines, and just know whenever we're dealing with a binary tree, we tend to be dealing with that implementation. When we talk about AVL trees, we will add a 4th field to this, which will be a height field, so we can store the height of that node. Don't worry about that for now, but we will be adding to that later on. But the idea will be that as we talk about these trees, if I ever write a binary tree out like this, just think, okay, this is how the implementation would be. But we're going to tend to discuss them by drawing these pictures, and you should just think of this as the equivalent. So that's a regular binary tree. However, we're not restricted to binary trees, though I say that's what we'll most commonly be dealing with. So the question would be, what kind of other implementations might we have? And let's consider that we might have a number of children, because that's the other possibility. A binary tree is restricted to 2 children, but you might say I could have any number of children. It might be a k-ary tree in which we have a certain set number of children, or a set maximum number, or it might be just a general tree where we have some varying number of children. And one node could have 4, and the next node could have 10 children, and there's no bound on that. And likewise, we can have an ordered or unordered tree, where the order matters or it doesn't. Generally, when we talk about k-ary trees, as soon as we get a maximum number of children, we're usually talking about an ordered tree as well. And the binary tree, for example, there's a definite left and right pointer to that. That's an ordered tree, and the order matters. But in general, we have even the concept of an unordered tree. The question is, when we have this varying number of children, how do we deal with it? And there would be 2 other ways that we could deal with that. We could have a node that contains your value and an array of pointers. And this would, I would think, be most useful for the k-ary tree when your concern is accessing a tree quickly. So this would probably tend to be more useful for a k-ary tree where we know the maximum number of children, but it could certainly be used for a non-k-ary tree as well. You would just have to recognize that if you are using it for a tree that has no bound on the number of children, you might at some point need to increase that array size and say, well, I have 5 cells in this array, but I now want to add 6 children, so I'll increase the array size either to 6 or to doubling the array size, as we talked about with stacks. But the idea there would be when the concern is accessing a subtree quickly, and this of course be by index, then this kind of node would be useful. Most likely, we'd come across this in a k-ary tree. The other possibility, of course, is to say, well, let's have a linked list instead. And so this would be likely to be used when your concern is inserting or removing subtrees or shifting them around. In other words, the same trade-off we had between an array and a linked list in general. Spots where the array would be useful in real life, having an array of pointers to subtrees would be useful in a tree node, and spots where a linked list would be useful in real life, depending on what operations you're most concerned with or trying to optimize. Those would be situations where a linked list of pointers would be most useful for a tree node. And so the idea is all these pointers are always pointing to subtrees, and same thing down here. It's just a matter of, well, are you more concerned about being able to rearrange and insert and remove from the sequence of subtrees, or are you more concerned about saying, given an index, grab a particular subtree really fast? And so then those are your choices there for implementation. And for a binary tree, since we only have 2 pointers, there's no sense storing a linked list of just 2 pointers. We say we'll just have variables for the pointers, and we'll have left and right. And if left is null or right is null, no big deal. Likewise, even if we had a 3 or a 4 array tree, we might find it suitable to actually build variables into the nodes and say, well, I have 1, 2, 3, and 4. Once we have any large number once we have any large maximum, certainly we would rather use an array or a linked list. But if you're dealing with, say, 3 or 4 pointers maximum per node, you may well want to just have separate variables like you would for the binary tree node itself, instead of having an array of 3 pointers or a linked list of 3 pointers. That almost seems pointless. No pun intended. The last thing to mention is that even if we have, or sort of keeping this idea of a linked list in mind, if we're going to have a tree node where we have a value and a linked list of subtrees, we could very well instead decide that we want to keep track of that linked list within the nodes. That is, this is often called the binary tree representation of an ordered tree. And the idea here is, let's say we have here A, and I have here B, X, C, and X has perhaps 2 children, L and W, and C has maybe 4 children. And they are D, E, K, and F. So again, whatever tree we happen to have. The idea behind the binary tree representation, we say, well, I need to have nodes with just 2 pointers. Instead of a node containing a whole linked list, I can simply have a node containing 2 pointers. One of them will be the first child pointer, and the other one would be the next sibling pointer. So for the root, the next sibling would be null because there is no root. There is no sibling of the root. For the first child, we point to the first child, and then that points to the next sibling. So that is, instead of having a node containing the root value and a linked list of children, we would instead have a linked list composed out of the children themselves, and that's what we're doing here. So here I would have the first child would be L, which has no first child of its own, and then that points to W, which likewise has no first child of its own. And then C would point to the start of a linked list, which has no first child of its own. D, and then we have here E, and so on. We have a linked list of 4 values there. But the idea is that your first child points to a linked list of your children. Your next sibling is how those linked lists are made. So B points to or X would point to its next sibling, which is C, and its first child. And we would build the structure like that. Or if I wanted to draw it without explicitly putting the pointers in the nodes, just take this and draw it out like this, where we say A, B, X, C, and then we have from X we have L and W, and D, E, K, and F. So that would be, this is our tree. This is how these 2 things would be how the implementation is set up. Again, here I just haven't explicitly drawn out the rectangular nodes, but you can tell what the pointers are meant to be from the picture. And so this would be how the implementation could work if this was our tree. And so that's known as the binary tree representation of an ordered tree, because we're building an ordered tree out of trees with only 2 pointers, or tree nodes with only 2 pointers each, as opposed to on the earlier slide where we had a tree node composed of a whole linked list of as many pointers as we needed, plus the element itself. And that's it. This is a, maybe I went a little fast, I don't know, but this is tends to be a shorter lecture. That is basically your whirlwind introduction to trees. We've got a bunch of definitions and an ADT discussion very briefly, and then implementation discussion. And what we'll talk about next time is tree traversals, and after that, binary search trees. And that's it. So we are done here, and I will see you next time.